All right.
So today we are very happy to have our new postdoc, Ghosh, who is going to talk about module spaces of instantons on asymptotical conical spin 7 manifolds. Let's welcome him.
Thank you very much. I'm delighted to give a talk, my first talk at NCTS, and opening up the seminar series. So I'm Ghosh, and this project is part of this program, which me and my PhD supervisor, Derek Harland, started, and we are still working on continuing this program even now. So this is kind of the structure of this talk. First, I'll talk about manifolds with exceptional holonomy. Then I'll give an overview of gauge theory in its original setting in 4 dimensions, and then explain these notions of instantons in this so on asymptotically conical manifolds. Of course, I will already explain them in section 1 what these manifolds are. So unfortunately, what I promised, the deformation theory, kind of I'll overlook that part because I rather focus on the background a bit more. At the end, I'll kind of give a very brief overview, but that requires a lot of spin geometry, which I'll say as little as possible. So let's start with the first part. Hopefully everyone here is familiar with the notion of holonomy. So I'll have my Riemannian manifold simply connected, oriented, non-locally symmetric, irreducible. And now the holonomy group is just, the group of parallel transports along any closed loop. And so it preserves the Riemannian metric, which means it will be contained in, so hol G will be a subset of SUN. So this S comes from the fact that I started with an oriented manifold. Now, so that's just Riemannian metric, right? Now I'll consider special metric, which will give special holonomy. So that's the Bayes classification. So special structures. Group and the dimension in which it can occur. Taylor, my holonomy group should be contained in UN. I have to consider even real dimensions. Calabi-Yau, I need my holonomy group will be SUN, again dimension 2n, hyperkähler. This will be SPN, now I need 4n. Quaternionic, Kähler. Now I need SPN dot SP1. This dot means cross quotiented by Z2. 4n. Now, G2 and spin 7, which are named after the holonomy groups itself. So the holonomy groups are G2 and spin 7. Now, instead of you see this n appearing, I'll have very definite dimensions 7 and 8. So these are all special holonomy, and these two are exceptional among them. So that's the idea of holonomy groups and manifolds with exceptional holonomy. So what are they? So I'm gonna introduce them by comparing with something that hopefully everybody knows, the SU3 structures on 6 manifolds. So Calabi-Yau manifolds or stuff like that. So review of SU3 structures. So now I have a 6-dimensional manifold, Riemannian manifold. I have a fundamental 2 form. I have a holomorphic 3 form. Right? I have these 2 things, 2 form and the 3 form. Now, we know that the manifold M6 is Calabi-Yau if we have certain relations involving omega and this capital omega. But the one I want to focus on is the fact that these are integrable, which means when I apply the Levi-Civita connection on them, they are 0. And it's the same thing as and, right? So that's the integrability of the structure. And then we'll know, okay, then the holonomy group is actually contained in SU3. Now there's another kind of manifold, which is nearly Keller. What happens there, I don't have integrability, which means, so I have a relation like clearly you can see, d omega is not non-zero, d capital omega is non-zero, and but they kind of control one another in this way. And there's a relation with existence of killing spinor on the manifold. I don't want to talk about that. But the point is, this is non-integrable. This is integrable. This is non-integrable. This is Ricci flat. This is definitely not Ricci flat. But suddenly, this will be able to capture a lot more examples, nice examples, which we know. For example, S6, CP3. These will be these nearly Keller manifolds. So now we are in a condition to talk about the G2 and spin 7 structures. So I just talk about the SU3 structure. Number 3, G2 and spin 7 structure. So compare with that situation and you will kind of understand what's going on. So now I'll start with a 7-dimensional manifold, Riemannian manifold. Now I'll consider a 3 form on it. And I'll call it a G2 structure. Can you see it down there? All right. So in a local orthonormal basis EI, maybe I should still do it. In a local orthonormal basis EI, I can actually write this 3 form as E1 to 7 plus E3 4 7 plus E. But I have used this shorthand EIJK is EI with EJ with EK. Right? So that's definitely a 3 form. Why I have written it this way? There are 2 reasons behind that. First of all, these are something called octonionic structure constants. So if I go back to this Bayes' theorem, you can clearly see this part somehow. So the Riemannian manifold, real, you have the complex here, you have the quaternions here, and this G2 and spin 7 will be controlled by the octonionic algebra. So these are so real complex quaternion octonions. These are all the normed division algebras over R, only these 4. So the G2 and spin 7 somehow controlled by the octonionic algebra. But I'll give another motivation behind exactly why I write it this way. Anyway, moving on. So there you can see, you could see I have like a 2 form, a 3 form. Here I have a 3 form, and I can, this gives a 4 form. Star phi, you see, right? So there I had a 2 form and 3 form. Here I have a 3 form and 4 form. Now, exactly like that, I'll call this sigma 7 phi a G2 manifold if Levi-Civita on this phi is 0. Alternatively, that's you can prove that this is the same thing as d phi equals 0 and d psi equals 0. Right? Exactly similar to this, the integrability condition. So if that happens, my manifold is a G2 manifold and the holonomy is contained in the group G2. Yeah, the 3 form does come from the metric. Okay, I'll show you, and then let me tell you the non-integrable rather definition, and then you'll see what's going on there. So now, just like this, if d phi is non-zero, rather you have something like d phi equals 4 psi, then we have nearly G2 manifold. So now this is the phi is definitely closed. So d phi equals 0 is satisfied there because, you know, apply d on both of them, you'll get 0. But phi, d phi is non-zero. So this is the nearly G2 manifold, exactly like the nearly Kaya manifold. Again, there's a story with existence of killing spinner in there and things like that, which I do not want to talk about now. So yeah, the 3 form comes from the metric, but somehow when you apply the Levi-Civita connection, it's not 0. There's a torsion. So it will be 0 with respect to something else, which we'll call the canonical connection. Okay, so what's the motivation of this expression? I'll start with my sixth manifold. Consider R6. Let me start with R6. Right? I can write down a 2 form and a 3 form this way. Right? So that's my R6. We know that it has the SU3 structure. What I'll do, I'll consider R7 as R6 cross R, 1 over R6, where this radial direction, I'll fix a basis E7. Then from this structure, I can get a G2 structure on R7. From the SU3 structure on R6, I can get a G2 structure on R7, where my G2 structure will be just the omega 0 with E7 plus imaginary part of capital omega 0. Now apply this on that and you will exactly get that one, which you can already kind of see it. So E12 plus E34 plus E56 with E7 and so on and so forth. So now my manifold is like locally this. So you can identify R7 with the tangent space and then orthonormal basis of R7 with orthonormal basis of that one locally, of course. And that's the justification behind this. Now that I have told you this cylinder thing, I won't write down the spin 7 structure that way. I'll just mimic this one and say I already have R7 with my 3 form. I'll cross it with R and then I have R8. I'll consider a 4 form this way. Again, I'll consider E0 to be the basis of that radial direction. E0 with phi plus psi. Remember, psi is the hot star of phi. So now, if I have a 8-dimensional Riemannian manifold and I have a 4 form on it, which in local orthonormal basis can be written like this. And of course, I need the integrability. So Nabla-Levy beta of this 4 form, which is 0, and that's the same thing as D of this 4 form is 0. Then this manifold is my spin 7 manifold. All right. Any questions so far? So I managed to talk about what are G2 and spin 7 manifolds by comparing them with the kind of more well-known SU3 structure. So that's basically the idea of G2 and spin 7 manifolds. Now I want to talk about this particular kind of non-compact manifolds called asymptotically conical manifolds. But before that, any questions about this one? Yeah? No, the metric and the three form will determine one another. Yeah. So they're definitely compatible. You can get one from the other. So when I write down the asymptotically conical thing, hopefully things will become more clear because I'll be more explicit with the construction. So remember what I did there just before that was the cylinder construction. In fact, that's not just R7, R8 with any, if you start with any Calabi-Yau and consider a cylinder over it, you will get a G2 manifold. And similarly on a G2 manifold, if you construct a cylinder on it, you will get a spin 7 manifold. However, there's an alternate. So instead of cylinders, putting a cylindrical metric on my manifold, I'm going to put a conical metric on it. So suppose I have a 7-dimensional Riemannian manifold with a G2 structure. Now I'm going to consider a cone over it. Where the metric I'll consider is, right, the conical metric. And so that's a 8 manifold. And now I can cook up a 4 form, a spin 7 structure. So that's what I said. One will determine the other. So R cubed dr with phi plus R to the power psi. Right? So now I have C sigma with this 4 form. I didn't say this was a G2 manifold. I said a 7 manifold with G2 structure. And now I have an 8 manifold with a spin 7 structure. Now, unlike the cylinder situation, we cannot have integrability on both directions. If I want this to be integrable, my starting G2 manifold, then the resulting cone will not be integrable. And vice versa. If I want this to be integrable, then this will not, which you clearly can see if I impose the condition that my d phi equals 0. Then you can actually from this expression calculate that my small d phi will be some constant times psi. Well, yeah, it will be. Which means in order to get an integrable spin 7 structure or the spin 7 manifold for the cone, I need to start with my nearly G2 manifold. And similarly, if I same construction works for nearly Keller and G2 as well. Fine, I have the cone. There's a conical singularity. I need complete manifolds. So what I can do, I can resolve that singularity, and then on the whole thing, I can put a metric which is very close to the metric on the cone. And that's the asymptotic relation. So I'll start with an 8-dimensional non-compact spin 7 manifold. I'll call it asymptotically conical with rate nu less than 0. If there exists a compact subset K of that 8-dimensional manifold, a compact nearly G2 manifold, sigma. I have some parameter are greater than 1, and the diffeomorphism H from this cone to my 8 manifold with the compact set removed. Right? So let me draw the picture here, which will help us later on as well. I have the cone. Suppose I have the projection onto my sigma. So this is my cone C sigma. This is the radial direction. 0, I pick some r here, this goes to infinity. So this part, let me correct it a bit. No, this was all right. Right. So this part was capital R infinity cross sigma. Now I consider that X with a compact set removed. So that's my X. With I have a 4 form phi here, and of course on the cone, I have the 4 form phi C, and a diffeomorphism on the upper part. So I remove the lower parts, here the K and here this 0 to R part, and I have the diffeomorphism between the two. All right. So when will I call this manifold asymptotically conical? The condition is with respect to the Levi-Civita connection on the cone, if I pull back that 4 form on x minus k to my cone and then compare with the pre-existing 4 form on the cone, and evaluate it at Rp, this should be of order R to the power nu minus j as R goes to infinity. So clearly, now forget about this j, think of the simple condition. So for j equals 0, so this minus this, both are 4 form and that's of order R to the power nu. So that's the asymptotically conical condition. So this is my asymptotically conical manifold. Basically, in practice, what we do, we start with the cone. There's a singularity. We try to find some compact manifold to attach to it, and then try to calculate a new metric which is very close to the old conical metric. That's it. Let me give you let me give you a few examples first. So you start with your 7 sphere, the very usual one. Consider the cone over it, and then attach just a single point. That's your R8. There's something called a squashed sphere. If you consider the Hopf vibration, the 3 part and 4 part, you squash the metric for the 4 part. So in terms of homogeneous spaces, you can write that as sp2 cross sp1 quotient sp1 square. Just think of a sphere with a different metric. Now you consider the cone over it, and then you need to attach a 4th sphere to it. And that's again an asymptotically conical spin 7 manifold, which is actually something called the negative spinor bundle on S4, or otherwise known as the Brand-Salomon spin 7 manifold. I'm gonna keep this here. So that's what an asymptotically conical manifold is. Now you can do the same with your G2 structure, and you will get something called asymptotically conical G2 manifold, where in dimension 6 you have the nearly Kähler. And there you have, of course, the example R7 and few other Brand-Salomon manifolds. For example, the spinor bundle of S3 and things like that. Right. Any questions about the asymptotically conical manifolds? Right. For these examples, you mean? Oh, the rate is new, right? So R to the power. So if I do this, I calculate what rate it is, and I look at the simple one where, this is just a 0. I see, okay, after the calculation turns out it's R to the power -2, right? Then I'll say, well, my asymptotically conical manifold is asymptotic with rate nu equals -2. Yep. Same rate. Same rate. So in this expression, if you substitute this 4 form phi by the metric G, nothing changes. So the metric and the 4 form has the same rate. In fact, same expression even. Right. So R8, any rate works. For this one, it's -10/3. That's asymptotically conical manifold. Now, non-compact. We need to do like Sobolev theory and stuff like that. We can do that on non-compact manifolds. Fortunately, on these asymptotically conical manifolds, there has been a theory which we can use to talk about like smooth sections and things like that. Let me explain that one. So start with my 8-dimensional, now it's asymptotically conical manifold. I consider a vector bundle on it with a connection compatible with the metric. So I suddenly started talking about bundles without any warning. There are certain bundles that will appear in my talk. One is the vector bundle and the other is principal bundle. And then when we'll do gauge theory, we need to consider connections and curvatures on them. Okay, anyway. So suppose I have a compactly supported smooth section of this thing. We know. So now I'll define the weighted Sobolev norm the following way. Right? So now if you compare with the Sobolev norm that you already know, you will see that only this term involving rho is what extra in here. And of course, this appearance of -8, you clearly see, okay, that's because of we're dealing with a manifold of dimension 8. So this thing is extra, which is there to ensure the convergence of your Sobolev norm. And so, of course, my rate is less than 0. So what is this rho? This rho is a real valued function on my manifold. We'll call it the radius function. The way I'll define it is rho of x will be 1 for that compact part, for this part in your x. Or somewhere up there, it will be just the radial function r, or my r is in like something like, so a bit, sorry, this part is 2r to infinity. So I start a bit high and consider everything from there. In the middle, when my x is in like r to 2r cross sigma, I'll kind of interpolate it from r to 1 in a smooth way. So that's my radius function that appears in the Sobolev norm. And I'll call it the weighted Sobolev norm, and of course the completion of CC infinity E with respect to that norm, I'll call it WKP nu of E. That's my weighted Sobolev space. Now this theory was first introduced by Lockhart and McEwen. Then for mainly a cylindrical case. Then the conical case appeared in this PhD thesis on the Joyce. It's called the deformation of special Lagrangians. There, the conical approach was formulated. And that's the go-to technique to do analysis on these asymptotically conical manifolds. So that kind of concludes the part 1, which is introducing G2 spin 7 and asymptotically conical manifolds. Any questions so far? Okay, so for the next part, of course, I'll be very brief and very hand wavy. This part I wanted to spend a lot of time on because I hope this will be actually interesting and helpful to many of you what you are doing in your own research. Now I'm a gauge theorist, which means gauge theory is the study of connections. Connections on what? Connections on some bundle, either principal bundle or vector bundle. So think of a principal bundle, principal G bundle. Here G is a compact, you may take it to be semi-simple Lie group. So this is a principal bundle. That means you have a fiber bundle where your fiber is this Lie group with some action of this group, some rule satisfying. So you can always cook up a vector bundle, which we call the associated vector bundle. I'll denote it by GP to take care of, to remember this, where I'll consider the Lie algebra of that Lie group to be my fiber. So this is the associated vector bundle, and you can easily prove that there's a one-to-one correspondence between the connection here and connection there, and corresponding curvature. So connection and curvature on vector bundles, you can just think of what you did for the tangent bundle, the Levi-Civita connection and the Riemann curvature, and kind of intuitively generalize that, where you don't just have your tangent spaces here, you have some vector space, which doesn't have to be the same dimension as your manifold. And then you have some connection and curvature here, which again, locally intuitively, you can think of them as some Lie algebra valued one form, Lie algebra valued two form, and so on and so forth. And they relate nicely. You can construct one from the another. So when I'll talk about connection or curvature, you can think of them on either of them. So suppose I consider this to be the set of all connections on my manifold X. See, I haven't mentioned any constant on the dimension of the manifold. This works for everything. Then the curvature of the connection, just I'm writing the expression for it, where you can write this as dAA, where dA is the covariant derivative d plus half A dot. Now, if you are not, like two same thing here, how is that not zero? Well, this whole thing is actually a two form. So AA, when it acts on XY, this notation means it's the Lie bracket of AX and AY, which will of course become zero if, so told you, these are Lie algebra valued. So if your Lie algebra is abelian, then that thing will be zero. So this part won't be there. Anyway, and there's a notion of something called gauge transformation. Okay, by the way, I called this connection, this curvature. In physics literature, this will be called gauge field or gauge potential, and this will be called field strength. And the gauge transformation is just a bundle automorphism. And if you consider the group of all gauge transformation, that will give you a group, the automorphism group, bundle of automorphism, of course, and we'll call this gauge group. And sometimes we will call this gauge group as well. There's a reason behind that. You can identify them time to time. Okay, so I have the set of all connections, and now I want to quickly talk about something called Young-Mills theory and instantons. So everything is in physics is described by some Lagrangians. So the Young-Mills Lagrangian, which takes a connection and gives you a 4 form on the manifold. Okay, let me fix my dimension of my manifold to be 4 now. So your connection goes to minus trace of the curvature with the Hodge star of curvature. Remember, dimension 4. This is also 4, 4, 8. Makes sense. So this is basically, right? That's my Young-Mills Lagrangian. Now the Young-Mills action is just the integral of the Young-Mills Lagrangian over the whole manifold. That's a functional. From whenever you see a functional, the first thing, of course, pops up in mind. What are the critical points? So if you apply the Euler-Lagrange on this, the condition that you will get is dA star of your curvature is 0. This is just the formal adjoint of dA, the one I wrote down. Right? And in particular, you can write dA star as minus star dA star. Just the formula joint of dA. That's Young-Mills equation. So the solutions of the Young-Mills equation are actually critical points of your Young-Mills Lagrangian, Young-Mills action, sorry. Now you can prove that there's an identity which always holds. That's the Bianchi identity. Right? So combining these two, you have the whole gauge theory. Take your gauge group to be U1. Then you can actually, it's a very simple calculation that these two equations are precisely the Maxwell's equation that you usually write down in terms of E and the electric field E and magnetic field P. In fact, Hodge actually came up with the Hodge star operator precisely so that he can write the Maxwell's equation in a very easy way. Okay, so how is this related to physics? I said you consider the U1 gauge group and that gives you electromagnetism. If you take gauge group to be SU2, that gives you the theory of weak forces. If you take the gauge group to be SU3, that gives you the theory of strong forces, and ultimately you got the standard model of particle physics. So that's the physics aspect of the Young-Mills theory in dimensions 4. Instantons. So I just said Young-Mills solution of Young-Mills equations are the critical points of the functional. So I'm going to consider a particular solution. So think of this equation, very algebraic. I'm going to call it instanton equation, and any A satisfying this, I'm going to call that instanton. Fine. So what's the special about it? Put that connection in your Young-Mills equation. So you're considering dA star FA. You know that star dA star FA. But now here, instead of star FA, you can actually put just FA because you start with an instanton. Now, what's dA FA? Bianchi identity tells you that's 0. So an instanton also satisfies your Young-Mills equation. Now, using Chern classes, which I'm not going to do, you can actually prove that the instanton doesn't just satisfy Young-Mills equation, is the absolute minimizer. So that's what instantons are. And there's again in physics a whole story about quantum tunneling and things like that. But I have some time to talk about dimension 4 is fine. I just talk about half of the talk for about dimension 7 and 8. Look at this equation. This equation makes sense in any dimension. What about this? The Hodge star is involved. You are going to take an n form, suddenly get k form, suddenly get n minus k form. Here you see in defining this equation, it's so crucial that the dimension was 4. If you take a Hodge star of a 2 form, you are going to get a 2 form back. So the way you write down these instanton equations in dimensions 7 and 8 is the following way. We're going to take help of the G2 and spin 7 structures. Remember, those are forms. One was 3 form, and the other was 4 form. So what I'm going to do, you need to count the dimension yourself. I'm going to say my G2 instanton equation is this one, and my spin 7 instanton equation is this one. Here the Hoster is the Riemannian metric of the, with respect to the Riemannian metric of the dimension 7. 2 plus 3, 5, Hoster of 5 is 2, makes sense. 2 plus 4, 6, Hoster of 6 in 8 is 2. It works. There's a lot of, so these instantons have infinite energy. So the L2 norm just, yeah. But it will satisfy that equation because your phi, small phi and capital phi are closed and co-closed. So d phi equals 0, d star phi equals 0, d capital phi equals 0. So using them, you can prove that these also will satisfy your Yang-Mills equation. So I do have time to talk about how these notions will look on the asymptotically conical manifold. By the way, I forgot to say one thing. I talked about, so you consider all instantons and then you quotient it by that gauge group I talked about. And that is your moduli space of instanton. So in dimensions 4, that works. So now instantons on asymptotically conical manifolds. So I consider a principal bundle on R8 and a principal bundle on sigma 7. Nearly G2 manifold, spin 7 manifold. They both appear there, right? Well, I erased the relation, but the asymptotic relation. So I have a pi here. So if I pull back the bundle on my cone, pull back the bundle Q on the cone, and on the other hand, pull back the bundle P on the cone, one using the pi and other using the diffeomorphism H. I'm going to impose the condition that they should be isomorphic. So that's how I choose these bundles. I can always choose. There's a lot of freedom. And then I'll consider a connection A on this bundle and another connection A sigma on this bundle. Now, I have this asymptotic nature of my asymptotically conical manifold where this sigma 7 is at infinity of your 8 manifold, right? So I want my instanton to exhibit the same similar nature where at infinity, my connection on my 8 manifold should converge to a connection on my 7 manifold. So I'm going to impose exactly the same condition that when I pull back my connection from the asymptotically conical manifold to the cone and then compare with the connection again on the 7 manifold to the cone, they should satisfy this asymptotic relation. Right? Again, I'll consider some sort of a notion of gauge group. Again, that will have this asymptotic nature. If I consider a gauge transformation, I'll impose that at infinity, it should converge to the identity in, of course, the weighted Sobolev norm. So now I can easily define the moduli space of instantons on asymptotically conical manifold the following way. I'm going to call this condition star. So I'm going to define this AP to be the set of all instantons A on P satisfying star quotiented by the gauge group. So the set of all gauge transformations exhibiting this kind of convergence behavior. And that's my moduli space, which depends on this A sigma because it converges to the sigma and the rate nu, of course. So that's my moduli space. Now my own results. I have these two manifolds in 1985. Frale, Nuits, Fubini, and Nicolau constructed instantons on R8 in the context of supergravity. So supergravity was very big at that time. 11-dimensional theory, and suddenly you want to construct this kind of gauge theoretic objects in dimension 7, 8. And recently, 2019, Clark and Oliveira constructed instanton on this manifold. So one of the results, a couple of results of mine is I actually calculated the dimension of the moduli space of these instantons. So when it comes to the FN instanton, so I call this FN instanton. So the virtual dimension of the moduli space of my FN is when the rate is minus 2 to 1, it's 1, and when it's between minus 1 to 0, it's 9. There's a reason behind that. So just like the manifolds have rates, the instantons have rates as well. And the instantons on these two manifolds turns out to have rate minus 2. And that's why we only need to look in the range minus 2 to 0. So that's for the FN. For the Clark Oliveira, the moduli space turned out to have dimension 1 when the rate between minus 2 to 0. Virtual. This refers to the fact that we still need to concretely prove that the moduli space is a manifold. There's a local argument called Kuranishi argument, deformation theory, exactly what I didn't talk about. We'll give you something like you need to prove it's a smooth manifold by showing that it doesn't have any obstruction. So that refers to something gauge theoretic, where the moduli space locally will look like the kernel of a Dirac operator. And so no obstruction means you need to show that the co-kernel of the Dirac operator isn't there. So this is what I calculated is actually the index of the Dirac operator, which is the dimension of the kernel minus the dimension of the co-kernel. So to say that it is actually the actual dimension and your moduli space is actually a smooth manifold, you need to show that the co-kernel is 0. And then everything will work out. In fact, that's my current project. How much time do I have to have? Well, technically I'm done. So yeah, so that's it.
Any questions or comments? Is it arbitrary principal bundle? Is it arbitrary principal bundle?
Arbitrary. Well, when I construct the general theory, yes. When I consider particular examples, they are very, concrete, not arbitrary at all. For example, for R8, I'll actually consider the trivial spin 7 principal bundle.
So the structural principal bundle is spin 7.
Yes, this one is not. For example, for this one, it will be a SU2 bundle. So your gauge group G will be SU2 for this case. And then that's not trivial one. No, sorry, I said something wrong. That's still, that's also trivial. So both of these cases, the principal bundles will turn out to be trivial, but they have different gauge group. This one, I'll consider the spin 7 gauge group. This one, I'll consider the SU2 gauge group. And
Okay.
yeah. So of course, for those two examples, my principal bundle is very concrete. There's, you can nitpick by saying, okay, how many trivial bundles are there by looking at cohomology classes and things like that. But basically, you can consider the uniqueness of trivial bundles. So I consider very unique principal bundles for those examples.
So do you compute the dimension by proving some asymptotic conical version of Atiyah-Singer index, or
You of course need it, but non-compact version. So for asymptotically conical manifolds, the thing that works very nicely, consider a closed disk, D2. You have the boundary S1. Now make that boundary go to, so that's your radial direction. Make that radius go to infinity. So your boundary now at infinity, and then that's your R2. So basically the trick I used is to say that my non-compact manifold is actually a compact manifold with boundary, where boundary at infinity. And there's Atiyah-Singer theory for that, called Atiyah-Patodi-Singer index theory, where you need to consider something called an eta invariant of the boundary, because it's a manifold with boundary. That's a very analytic thing. Yes, I do need that. And there's another thing happening. You can see there's a jump in index because it crosses the point -1. That's something called the critical rate, where for that rate, the dimension of the kernel will blow up. So you need to remove that one. And that's why the dimension jump. So you get a family of Dirac operators, of course.
Say this Moduli space is a smooth manifold. You want to prove that? Is that what it is? You
Yes.
don't know that yet.
No.
And you can sort of do the same. I guess. What if you have a manifold that is not asymptotically conical, say something closed, or this? I imagine it's a simpler case, right?
No, that's the thing. Compact manifolds are for 7 and 8 are even more complicated. You cannot write things explicitly. I mean, think about writing a Calabi-Yau metric explicitly. Compact manifolds will always give you trouble. Non-compact manifolds are the simplest when it comes to writing down things explicitly. The analysis is the most complicated part, whereas for the compact, analysis is easier than this.
Right.
It's
But I mean,
reverse, yeah.
okay, you don't have any explicit formulas, but you still
No, okay, so I
can
didn't
define
write it.
everything.
No, I didn't write it down. It's very explicit. You can write down the instanton very explicitly.
What I'm saying is you can define the model. You can define instantons on a closed manifold as well, right?
Yeah, there are many.
You can define the Moduli space on a closed manifold as well.
Yeah, of course.
So in the closed case, the Moduli space, do you know it as a manifold? Or is it also not?
No, that's also not known.
In this case, do you have any kind of like compactness result? Or say you have a sequence of instantons with the functional is uniformly bounded or something like that. Do you have any?
Well, that's the thing. This kind of study is very new because, as I told you, physicists first came up with it like 40 years ago, but they didn't have any mathematical tool to actually deal with this. The Lockhart-McEwen analysis that I wrote down is a pretty new one, and somehow mathematicians thought, well, we could use that to study these objects. In fact, Brand-Salomon manifold was the negative spinor bundle of S4. That was the first non-compact G2 or spin 7 manifolds with full holonomy. So and that's 1994, I think, that paper. So it's a pretty new field, and a lot of things are not known. And the analysis is also very different from what you expect from analysis on compact manifolds, as you just saw, the very rate dependent analysis.
Okay. Any questions or comments? If not, let's thank Tata again.